Okay, it's time to get started. So welcome everyone in our fifth recitation of this semester. And today we are going to try to solve some problems related to sets, which is what we covered in the recent lectures. Apart from that, I'll also make a couple of announcements, and I have three problems ready that are on the quiz 2 material that I wanted to practice as well, because quiz 2 is coming up next week. Okay, so let me make a couple of announcements. So we're in the process of grading homework 2, which was due last week, and we should be done with that in the next 2 or 3 days. Then quiz 1 scores are out. As a reminder, you have 1 week from the time that we release the scores to request regrading through Gradescope. So I think we released this. We released the scores on Sunday evening, so you have until this coming Sunday to ask for regrade if you think something was not graded correctly. Then quiz 2 is going to be next week. So the same as last time is going to be on Tuesday, and you'll have a 1-hour window between 7:30 a.m. and 4 p.m. And quiz 2 will be on proofs. So only the material that is covered in section 2 of the books will be in quiz 2. And so sets, for example, will fall under quiz 3 and not quiz 2. One thing that I want to stress out is that students typically find quiz 2 to be the hardest. So make sure to prepare it accordingly and to study a lot for this quiz. I would also like to stress out again that you should definitely, if you haven't done it already, or if you want to remind yourself, read the syllabus and the announcements about the quiz, and also the procedure for taking the quiz and submitting your solutions. So quiz 1 was kind of a weird one because of the storm and so on, and so we were lenient in terms of how we were accepting solutions and so on. For example, we accepted a lot of solutions that were emailed to us instead of submitted to the Gradescope. In quiz 2, that's not going to happen. So for quiz 2, you have to make sure to submit your solution to Gradescope. You have to make sure that you tag your solutions for each question in Gradescope. So again, quite a few students did not do that for quiz 1, and then TAs did it manually, and we did not deduct points. In quiz 2, if you don't tag your solutions, you're going to lose 20% of your points. To facilitate submission through Gradescope, we increased the time for submission from 15 minutes to half an hour. So that should give you plenty of time to scan everything, take photos, whatever, and upload into Gradescope. So that's quiz 2. And then homework 3 is also out. It's going to be due on Friday, October 9th. So after quiz 2, we want to give you plenty of time to work on both. Okay, so these are the announcements I have. Any questions about these announcements? About quiz 2, anything else? Okay. Okay, so let's get started with a couple of review problems. And those are the kinds of problems that you might see in your quiz 2. So here's the first one. So it's a simple proof by contradiction. So we want to use proof by contradiction to show that there are no two integers x and y such that 24x plus 12y is equal to 1. So what is our proposition here? The proposition is that there are no two integers x and y such that 24x plus 12y is equal to 1. So in the proof by contradiction, we want to assume the opposite of that, and then we want to derive a contradiction. So what is the opposite of this? The opposite of this is that there exists two integers x and y such that 24 x plus 12y is equal to 1. And we are saying that this integer exists. So x is element of z and y is an element of z. And now we want to try to derive a contradiction. And in this case, that's really simple. You can do it like in 1 or 2 lines. So how do we do it? We divide both sides of this equation by 12. And so we get 2x plus y is equal to 1 over 12. Okay. So we know this. And then from the fact that x and y are integers, we also know that 2 times x plus y is also an integer. And this follows from closure of integers under addition and multiplication. Okay, so these two facts contradict each other. So one is saying 2 times x plus y is an integer, and the other one is saying 2 times x plus y is a rational number, 1 over 12. And so we reached a contradiction here between these two facts. And that concludes this simple proof by contradiction. Any questions? Okay.
Oh, there's a question from the chat. The question is, I thought that the contradiction was when we did P and not Q.
So Lynn, I apologize, but I cannot hear you. I think the problem is on my end. For some reason, my speakers are not working and I'll have to resolve it later. So I'll just read questions on my own. Thanks for helping and sorry about this. So great question for Adriana. And I got the same question in the previous recitation. And this is precisely why I actually chose this proof by contradiction. So the question is, I thought that contradiction was when we did P and not Q. So let me try to explain this. So most proofs by contradiction that we did in the past, the proposition was of the form P implies Q. In this case, okay. And then, we would assume P and not Q. And from there, we would try to derive a contradiction. So that's what we've typically done in the past. Now, in general, the idea behind the proof by contradiction is that if you have some proposition R, you have to assume not R. And from there, you have to derive a contradiction. So that's the general structure of proof by contradiction. And this general structure matches this particular proposition here, because in this proposition, we don't have an implication. We just have one statement. There are no two integers x and y such that 24x plus 12y is equal to 1. So that's our R. And then we start with not R, and we derive a contradiction. Now, how are these two connected? Well, this one on the left is a special case of the one on the right. Why? Well, because negation of P implies Q is in fact equal to P and not Q. So the structure on the left is just a special case of the structure on the right. And because here we don't have an implication, we just use the one on the right. So I hope that answers your question. Okay. Any other questions about this proof? Okay. So let's then do another one. So this is a proof by induction. Induction is kind of one of the most important proof techniques, and I mean, you can almost certainly expect that there'll be a proof by induction on the quiz. So I want to prove using induction that for each integer n greater than or equal to 1, 5 divides n to the power of 5 minus n. And I give two hints here. First, I give you a hint how to expand something that matches this. So if you have x minus 1 to the power of 5, it gets expanded into this big expression. I won't expect that you know things like that on the quiz. You should definitely know by heart how to expand x minus 1 squared, for example, but x minus 1 to the power of 5, you don't have to know by heart. Another hint that I give here is that you should start this by doing inductive hypothesis for n minus 1, and then the inductive step for n. I think this makes this proof a little bit easier. So those are the two hints that I give you. Okay, so let's do this. So what is the predicate we want to prove? So we want to show that for n greater than or equal to 1, n to the power of 5 minus n is equal to 5 times some p, where p is an element of z. So this we want to show. So this follows from the division theorem. This bar here is divides. Okay, so let's note down the structure of our induction. And one thing I want to mention here is that we will certainly be giving partial credits for your solutions in quizzes. And when you're doing a proof by induction, you know, even if you don't manage to do maybe the proof completely and so on, make sure that you at least note down the structure of the proof by induction. We'll be giving out points for sure if your structure is correct, even if you didn't manage to complete the proof, because structure is kind of almost the most important part. So here's the structure. Base case. In this problem, we do base case for n is equal to 1 because it starts there. And in the base case, we have to show that 1 to the power of 5 minus 1 is equal to 5 times p. So we get 0 is equal to 5 times p. And that holds when p is 0. And so we showed our base case. Then we have inductive hypothesis. And in case of this problem, I gave you a hint from where to start. Usually you won't get such a hint. So you can either start with n minus 1 and do inductive step for n, or start with n and do inductive step for n plus 1. I actually prefer the latter. But in this case, I think starting with n minus 1 and doing it for n works a little bit better. So what is our inductive hypothesis? It's that n minus 1 to the power of 5 minus n minus 1 is equal to 5 times some q, where q is an element of z. So we're assuming that our predicate holds for n minus 1. And now in the inductive step, we want to show that it holds for n. So we want to show that n to the power of 5 minus n is equal to 5 times some p, where p is an element of z. Okay, so how do we show this? So let's start with our inductive hypothesis and see how from there we could get to proving our inductive step. So in deductive hypothesis, we have this n minus 1 to the power of 5. So let's use the hint that I provided you to expand this. So then you get n to the power of 5 minus 5n to the power of 4 plus 10n to the power cube minus 10n squared plus 5n minus 1. So that's n minus 1 to the power of 5. And then we still have minus n minus 1. Okay. Let me put this in parentheses so that it's clear what is what. Okay. And from here, we want to show something about n to the power of 5 minus n. So we somehow want to see what n to the power of 5 minus n is equal to. And if we look at this big expression, you can see that we already have n to the power of 5 n minus n in this expression. So let's see what they're equal to. So if we move things around a little bit, we have that n to the power of 5 minus n is equal to, we should move everything else on the right hand side. So we have 5 n to the power of 4 minus 10 n to the power of 3 plus 10 n squared minus 5n, and this 1 cancel with this plus 1. Okay, and then from here, then we have that is equal to 5 times n to the power of 4 minus 2n cubed plus 2n squared minus n. And that is now equal to 5 times some p, where p is an element of z, because of closure of minus plus multiplication. Okay, so we showed that n to the power of 5 minus n is equal to 5 times some p. And so we showed our inductive step holds using hypothesis, and this concludes our inductive proof. Any questions about this proof? Okay. Okay, great. Make sure to practice proofs by induction. Make sure to understand the structure. That's really important. Okay, so one last review problem that I have is one that uses our pigeonhole principle. So we want to show using the pigeonhole principle that given any 7 integers, there will be 4 for which the sum of the squares of those integers is divisible by 4. Okay. And then as a reminder of the pigeonhole principle, so if we have m times n plus 1 objects and are distributed among n containers, there must be some container containing at least n plus 1 objects. So let's plug in some numbers into this to see how many containers we need. So we know that the total number of objects is 7, excuse me, because we have 7 integers. So m times n plus 1 is equal to 7. And there must be some container containing at least n plus 1 objects. So in our case, n plus 1 is 4. Which means that m is equal to 3. And if we plug this in into here, we can compute that n is equal to 2. So we need two containers, okay? So we need two containers, and we'll be placing these 7 integers in the two containers. And we know there'll be at least one container that has at least 4 of these integers. Now, whenever we're doing a pigeonhole principle proof, we have to define how are we placing these integers in these containers, or objects in containers in general. And that's where the hardness of this proof comes into play. There is just no really great cookbook for how to do this automatically. So specifying how to place objects into containers requires some thinking, some trial and error, and so on. And so, in this case, we want to prove that it's divisible by 4. We have 2 containers, we're placing integers. We know that each integer is either odd or even. So a good guess would be to place all even integers in this container and all odd ones in this container. Okay, and now we have to show that once you place these integers, there will be 4 in either of these containers, such that the sum of the squares is divisible by 4. So you will have 2 cases here. So case 1 will be when you have 4 even integers, and case 2 will be 4 odd. Case 1 is 4 even. So when you want to show for each of these cases that their sum of squares is divisible by 4. So let's do that. I'll kind of start a little bit, and I'll let you guys finish both of these cases. So case 1. We want to show that, let me think, let's say 2a squared plus 2b squared plus 2c squared plus 2d squared. We want to show that this is divisible by 4. We can do this just directly. We've done this many times before in different settings. And then we have case 2. We want to show that 2a plus 1 squared plus 2b plus, sorry, let me erase this. Plus 2b plus 1 squared plus 2c plus 1 squared plus 2d plus 1 squared is also divisible by 4. And here, A, B, C, and D are element of Z. And the same thing holds here. So A, B, C, and D are element of Z. Okay. So this should be easy to show. So I'll give you a couple of minutes to prove these 2 cases. And then I'll split you guys into breakout rooms. You can discuss amongst each other how you would go about doing this. And then I'll finish it for you as well. And it should be really easy. So I'll just give you a couple of minutes. Hey, Lynn, could you try saying something? I'm just curious if I can hear you now.
Can you hear me now?
Okay, yeah, I cannot hear you. I'll have to figure this out. It's okay, thank you. I'll figure it out after the lecture.
Yeah.
Okay, welcome back, everyone. I hope you managed to do the proof, but let me also quickly do it for you. So the first one is a little bit easier, case one. So you just have to square all these things, and let's see what happens. So we get this is equal to 4a squared plus 4b squared plus 4c squared plus 4d squared. And that is equal to, we pull out 4 times a squared plus b squared plus c squared plus d squared. And that is then equal to 4 times some k, where k is an element of z. And this follows from closure of what do we have? Addition and multiplication. So that's case one. Case two is the same structure, maybe just a little bit trickier because it's a little bit harder to square these things. But so you get 4a squared plus 4a plus 1 plus, there is a clear pattern, 4b squared plus 4b plus 1 plus 4c squared plus 4c plus 1 plus 4d squared plus 4d plus 1. Now we group this a little bit. So that is equal to, actually, you can see right away that you can pull out 4 because we have the squares that all have 4 next to them. Then we have just the symbols with 4, and then these 4 ones add to 4. And so if you pull out 4, you get 4 times a squared plus a plus b squared plus b plus c squared plus c plus d squared plus d plus 1. And then that is equal to, similar to the previous case, 4 times some k, where k is an element of z. And that also works because of closure of addition and multiplication. And then this concludes our proof. So we show that in both boxes, when you pick 4 integers that are in them, you get that their sum of squares is divisible by 4. Okay, any questions about this proof? So there is a question from Chung. And sorry if I'm butchering your name. Sometimes it's kind of hard to pronounce based on just spelling. So there is a question about, there's 7 integers, and in real life we can distribute them to case 1 even, case 2 odd, case 3 even number and odd number together. Why is n equal to 2 in this situation? So n is the number of boxes, and the number of boxes has nothing to do with the fact that these are integers. So you can derive n by just imagining that you have 7 objects and you have to distribute it into boxes so that there is at least 4 in one box. And so from there, you can derive how many boxes you need. And then once you derive how many boxes you need, only then you try to come up with a strategy for how you are going to place objects in these boxes. So that's how you know that you need 2 boxes. Any other questions?
Can we try to do another example?
So, I mean, Pigeonhole principle can be kind of tricky. And so if you are really confused about it, please come to office hours and we'll work on you one-on-one to try to clear up any misunderstandings or confusions you have about it. Okay. Good. So let's now do some problems involving sets. So in the lectures, we introduced a bunch of definitions related to sets. And this is just an incomplete reminder of those. You have to know what a subset is, proper subset, when two sets are equal, and so on. So make sure to know all of these definitions. Without them, it'll be hard to solve problems using sets. We also introduced an empty set. There are 2 ways to denote it, either using empty curly braces or using this symbol. It kind of looks like a 0, but it basically, it's a crossed circle. We also introduced the universal set, which contains all possible elements and so on. And so, thank you, Lynn. Yeah, sorry, I had the same problem in the previous recitation. And I actually love when you guys unmute yourselves and ask questions directly without using chat. But today, something is somehow messed up with my speakers, and so I cannot hear you. And I really apologize for this. I mean, I tried different options and I couldn't make it work. So I'll fix this for the next recitation for sure. But today, unfortunately, you'll have to ask questions in the chat. And I'm really sorry about this because, like I said, I kind of like hearing your voice basically. But today it's not going to happen. So sorry about that. And thank you, Lynn, for making this announcement. Okay, so let me show you the problem. And I really like this one because it really stresses out, these definitions of various operations and their intricacies and so on. I like putting problems like this in the quiz about sets. So not the next quiz, but quiz 3. Because I think, like I said, it checks for your understanding of all these operations. So here's the problem. So suppose you have this set A, and here it's its definition. And you have to indicate whether each of the following statements is true or false by just circling T of F beside it. So we have a number of statements referring to this set, and you have to decide whether they're true or false. One thing to be careful about, I mean, some of them are kind of tricky, and you should be careful about curly braces. So you should be careful about, what is a set of sets, or what is a set and what is just an element, and so on. I think keeping them in mind will help you get this right. This problem always generates super interesting discussions. So let's do breakout rooms again, and please discuss, as you're going through these, please discuss the solutions among yourselves, because some of them are kind of tricky and I think really interesting. So let's do this again. And then I'll go through it and we'll do it together. So I just got a message from Austin. The question didn't stay up in the breakout room. I'm so sorry about that. I didn't realize that is going to disappear. So I'll keep that in mind next time we do this. So I apologize for that. Thanks for bringing this up, Austin. Okay, so let me do this. Like I said, I think it's an interesting one. You have to be careful. So part A, is 2 an element of A? That's clearly true because 2 is right here. Is the set containing elements 2 and 3 and a subset of A? So how do we show that it's a subset? Well, both 2 and 3 have to be elements of A. So we know that 2 is an element of A, we have 3 is an element of A, and so this is true as well. Okay, now things get a little bit trickier. Is empty set an element of A? So is empty set an element of A? Nope. So this is false. Be careful, this first element of A, it's not an empty set. That's a set that contains an empty set. So be careful about curly braces. So the next one is a set that contains an empty set, a subset of A. So this is true when empty set is an element of A. So we already know that empty set is not an element of A, and therefore this is false as well. Is the size of A equal to 3? How many elements does A have? 1, 2, 3, 4, 5. So A has 5 elements. So this is also false. The size is not equal to 3. Is an empty set an element of a power set of A? So if you remember, power set of A is the set of all subsets of A. So empty set is going to be an element of any power set. So this is true. Then is the set that contains set 2 an element of power set of A? So it's a set of all subsets. And so set that contains 2 is an element of A. That means that this is indeed a subset. So this is true as well. Is the set containing 2 and 3 an element of a power set of A? So is set containing 2, 3 a subset of A? Actually, we already had that under B. So B is true, therefore H is true as well. And then is the set containing 2, 3 a subset of power set of A? This is false. That would mean that 2 is an element of a power set of A. And we know that is false right away because power set of A contains only sets. And the last one is this pair set of 2, set of 3, an element of the Cartesian product of A with itself. So that's not true because these are not elements of A. So that's false as well. Okay. Any questions about this? I think the general kind of advice here is be careful about curly braces, right? Something like this is not equivalent to this. Same goes for, something like this is not equivalent to this. Let's see, questions quickly. Can I explain I? Okay, so in I, the question is the set containing elements 2 and 3 a subset of the power set of A? So if you remember the definition of a subset, that would mean that 2 has to be an element of a power set of A. and 3 has to be an element of power set of A. And neither of these are true, because power set of A contains all the subsets of A. And 2 and 3 are not even sets, right? So this is trivially false. So I hope that helps to explain I. Any other questions about this? Okay, so in the interest of time, I have to wrap up now. If there are some of these that are still confusing to you, you don't quite understand why the answer is true or false, please come to office hours. We can go through each of them individually with you and kind of more carefully and spend more time on each of them. So I'll stop here. Thank you all for joining. There is lots of office hours between now and the quiz. Please, take advantage of those. Make sure to practice proofs for the quiz. Make sure to understand induction, proof by contradiction, contrapositive, pigeonhole, direct proof. All these things will likely be in the quiz. What else can I tell you? There is also the tutoring center. So in addition to all the office hours, you can also seek help in the tutoring center. Okay, I'll stop here. That's it for today. Thank you all for joining.